I want you to help me out too. I don't, this is going to sound like an ego thing again, but it's something that I have to recognize about myself. We're all different as individuals, right? We're all very different. And we all learn differently. Like I said, it's not, education is partially science, but it's also an art form. It's you figuring out how you learn best and me figuring out how you learn best. And we may not agree on what we see. Somewhere's the truth. You know, we all need to be sharpened. We all need to be changed. I need to be changed as a teacher. I shared with you that one of the things that's frustrating for me is that after having taught this class for so long, I know it. And sometimes it gets frustrating for me on things that I think are really simple concepts. And you're going, I've never heard anything like this before. Help me. I'm drinking from a fire hose, right? We'll get through this together. I need you to remind me, but we've never heard that before, Mr. Baker. This is new to me. Oftentimes I'll see that in your eyes. But sometimes I'll keep on going because I'll say, well, obviously we don't need to cover that. And I'll go into things that I think we do need to cover. I also know that I have a large vocabulary. I use words sometimes again. It struck me when I took my entrance exams for the doctoral course I'm in, and it hits me when I get my weekly feedback from Grammarly. It's a plugin that I use to check my grammar, and it tells me how many unique words I use that other people don't use. So one of the skills you need to develop as a person, but especially as a teacher, is to learn how to speak in the context of the people you're speaking to. What did I just say? I used the word context, right? What does that mean? I need to learn how to be understood by the people I'm trying to speak to communicate with. It doesn't, do you notice when you go to the elementary wing, let's say maybe you're a teacher's aide, you're helping out somebody and you're dealing with a toddler, do you speak the same way to them that you do a middle schooler or a high schooler or an adult? No, you know intuitively to shape it a certain way, okay? So my familiarity with the material and my vocabulary will tend at times for me to say things that I think are easily understood because they're very precise, but that vocabulary word might not be part of your vocabulary list that you've covered up to this point in your life. I need you to go, whoa, stop. You think I should know that word, I don't have a clue what you just said, and let me help you out. That'll help me become a better high school teacher because I am kind of geared towards college level teaching. That's kind of where I'm at. That's part of why I'm so passionate about helping you prepare for that. Even now, if you wait till next year to prepare, really, you've started thinking way too late. You need to be preparing this year so that next year you can start implementing your plan for the following year. Don't wait till next year to get ready because you can't do it in simply 1 year. And so I will encourage you to experiment, for you to tell me, I learned this better this way. Is it okay if I do this instead? Like even today when you said, can I use index cards rather than the Frayer cards? Absolutely. I was going to tell you that module 2. You're free to use the Frayer. You're free to use index cards. I want you to show me, though, if I do a notebook check, I need to see that you're actually doing the work. You're putting your index cards together, so include that with your turn-in. Let me see them. And all I'm looking for is that you're making the effort. I'm not giving points simply for effort, but at this point, I need you to develop a habit of effort that'll produce results that we both want to see. Ultimately, I'm trying to help you get the material, understand it. I'm sympathetic to the amount of time you put in to get it, but frankly, some of you are going to have to work a lot harder than others in here. It's just the nature of a more difficult class. Not everything is intuitive. Okay? You're going to have to apply yourself sometimes. Certain modules will be easier. Those of you that have a good bent towards math, it's going to start off to be easier. Okay? When we get to certain chapters that are conceptual, some of you are visual learners, some of you are auditory learners, and I don't believe in strict learning styles, but understand it's good for you to get outside of your learning style once in a while. In fact, it's better for you to get outside of your learning style and you learn more in that way. So we're going to jump back to where we were yesterday. We were kind of short because of the lack of planning on my part for the chapel day being so much shorter. Every time I've taught this course here at the school, I have not had to deal with chapel schedule because Mrs. Cahill always kept my chemistry period the full period. That's why first period was so long, even on chapel days. She preserved that time for me, so I've been spoiled. Yesterday when the bell went off, I watched myself on video go, is that a fake bell or is it a real bell? No, it's a real bell. Okay. All right. We'll deal with that. So yesterday we were talking about matter. We said that you're made of matter and you matter, right? And we talked about fish. Do they understand that they're in water? When apparently some of us have a difficult time understanding that we are in air, that there's matter all around us, And that's one of the flaws we have as human beings. We tend to think that things exist only because we can see them, as opposed to they exist and we may or may not be able to see them. So this idea of matter, and ask this question: what is all around us but does not take up space and has no mass? What is there? Just think about it. It's a concept. What's all around us right now that doesn't take up any space? It doesn't have any mass. Can you think of anything? Now, before we did our little experiments and talk yesterday, you would have said air, maybe. Some of you, right? That's not true. But there is something around us. And we mentioned just a moment ago the difference between chemistry and physics. Physics is primarily mathematical. Things tend to go towards a formula that you then compute. Why? Because physics is about light. So light is all around us. We will talk about light. We will use frequencies of light during chemistry class, but only how it applies to chemistry. When you get into physics, then you start talking about light. Okay? As Pascal said, I believe it was Pascal, physics is science. Everything else is stamp collecting. Okay? Because there's a line there between what we call science and math as pure language, as pure knowledge that philosophers of science wrestle with all the time. So just be aware that light is all around us, and we're not going to talk about whether or not it has mass or not, because is light a wave or a particle? The answer to that question is yes. Light is both a wave and a particle, and yet we understand it as a particle that has no mass. So there are parts of this class that are beyond the scope of this class. There are certain generalizations that we're going to make. And so for this one, I'm going to tell you for right now, we're going to just consider that light has no mass, and it doesn't take up any space. All right, so I'm going to put these cues on here every now and then. It's not so you get to see what class you're in as if you forgot, or my name because I'm so great. It's really just so in your notes you know where we're at. Because each one of the major sections, right now if you were to look on page 4, units of measure, this lets you know, hey, Mr. Baker's now talking in that section, units of measure. There is no, for right now, unless you show me that you're not doing the reading, there is no expectation that you're going to read sections and take the notes on it, though it did help a lot of students. Though I would encourage you, if you're so inclined, to read in advance of the classes, take notes in advance of the classes, so that when you come here, we're reviewing rather than you learning. I'm not the only source of information for this class. The textbook is primary. I support the textbook. Okay? So read the sections. As I cover it, you should have either already read it or be reading it. All right? So that's just the basic understanding. But what I do is so that you in your notes know where I'm at, that if you get a little bit confused and you're afraid to go, I don't get it, or you don't want to slow down the class, you can at least remember, hey, this is the section we're in. This is where my question was at. And in this whole section about units and using units, there's just really one point I want to make. This is in the book. It's in blue, so it's something you need to know, memorize, that if you answer a question or solve a problem and do not list units with the numbers, your answer will be considered incorrect. If I were to tell you, part of my background, in college I was on the full contact karate team, and that I have a critical radius of my kick, and I'm making this up because I don't know what it is, but if I told you that my critical radius of my kick was 4.5 feet, if you're within 4.5 feet of my feet, you're going down. Okay? Now I asked you, how far away from me are you going to stand? Okay? If you say 5, without telling me feet, you could mean inches. I jokingly tell people that if you have no units on it, I'm going to assume it's Smurfs. Okay? Very seldom will the answer be Smurfs. It might more specifically be Papa Smurf, but it's never going to be Smurfs. And if you don't include units, I will say that's an implied Smurf, and it will be wrong. It's important because the fact that you say that something is worth 3, or the value of this is 3, as opposed to 3 cubic centimeters, or 3 meters, or 3 grams, it matters. The units matter. So a what I'd say, the coefficient or the units with, or the number without units is going to be wrong every time. You need to tell me how many of what. That whole section now, moving on to the metric system. You all familiar with the metric system, right? I was told when I was your age that I might as well forget the English system because everything's going metric. There's no real need for me to do that. So we study metric, study metric, study metric. Now it's what? 35 years later, and we still use miles, pounds, ounces, all those things. We're just kind of resistant to that change. But the vast majority of everything we do in this class is going to be metric or converted from English to metric. So, in talking about the metric system, first thing we want to talk about is this concept that mass is not the same as weight. That is one of the most common mistakes that students make. They think of mass as weight. And part of the reason is, yesterday when we did that experiment with the balloon, and we put the balloon on the triple beam balance, didn't it look like a scale? Didn't it look like we were weighing it? And truth be told, which is a fancy way of saying to tell you the truth. Sorry about that. But when we weigh those things, when we put them on a balance, we are actually weighing, but there's a nuance to that. There's a little way you need to understand that or think about that. That mass is not the same as weight. Mass is the measure of how much stuff, remember that very technical, very precise term called stuff? The stuffness of something? Mass is a measure of how much stuff we have. When I take your mass, if we put you on if we had a balance that we could put you on that could handle the scale that you're at, you know, and we were to find out how much mass you have, that would be a measure of how much stuff makes you up. If I take your weight, however, weight is a force. Weight is the amount of force that gravity exerts based upon your mass. So you see they're directly related. If you're one of those folks that go to the weight room, you understand that a pound is how many kilograms? Okay, 2.2 kilograms is a pound. Is that right? Yes. 2.2 kilograms is a pound. So when you do your conversions, when you go back and forth, you can say I can relate a kilogram to a pound, but they're not technically the same thing. A pound is a weight measure which says how much the Earth attracts or pulls down on that much mass. So here's the deal. If I were to be on Earth and suddenly, using Star Trek technology, beam myself to the moon so that I could be up there during the total eclipse on Monday and wave down at you as I went by, the gravitational pull of the moon is 1/6 the gravitational pull of the Earth. So, that's not me. But while I'm on the Earth, this little guy weighs 100 pounds on the Earth. But if he were to beam up to the moon, he would weigh 16.6 pounds. But he's got the same amount of stuff. Okay? So your mass is how much stuff makes it up, or you up, or the thing up. The weight is the force of gravity on that much stuff. So if we were to take that triple beam balance and take it to the moon, it wouldn't work correctly because it's calibrated for the gravitational pull of the Earth. We would need a different tool, or we need to recalibrate it for the moon. But the concept is we don't go to the moon to take the mass of things, we do it here, all here on Earth. And so we're actually using weight to determine mass, but it only works on the Earth. But if we took the mass on the Earth and then transported it to the moon, like when that's why these kind of phenomenon happen. Jumping on the moon, jumping on Earth. The gravitational pull is 1/6 the pull on the moon as opposed to the Earth, which is why the person with the same mass can jump so high, can go so far. They haven't lost any of themselves. They haven't gained anything and absorbed it into themselves. It's just the pull of the body is different. Okay? So as we consider the metric system, there are some basic units. For mass, and this is going to correspond with actually, let's see. On table 1.1, so this right here is all on table 1.1 on page 7. But the basic unit of mass, how much stuff, is a gram. If we were to convert that to the English system, that would be a slug. Again, slug's not a snail without a shell. It is a unit of measure that is a measure of mass in the English system. Remember, the English system is that system you're kind of used to. I grew up near Canada, and so when they invented those cars, they had a little button that you could switch back and forth between miles per hour and kilometers per hour. That was really cool for me, because as I was driving along, I always had to do the math in my head. Am I speeding or not speeding in Canada? Because my gauge was in miles per hour. But when this came along, boom, switch back and forth. One gauge was in English system, miles. One gauge was in metric system, kilometers. So those are the two systems. On all four of these slides, it's the metric system and then the English system. So mass is in grams and slugs. Volume is in liters and gallons. Primarily, we're going to be using liters. We may need to convert from gallons to liters or convert from liters to gallons, but our math is going to be primarily in liters. Again, this is table 1.1. Distance, the basic unit is the meter, the metric system, and distance in English system is based on the foot. And time for both is the second, so you don't have to convert back and forth. The unit of measure is the second. We talk about manipulating units, and what we're talking about here is based upon the prefixes in the metric system. I've got a recreation here of table 1.2. It's in your notes on page 8. One of the nice things about the metric system is you have a base unit, and that base unit is modified by the prefix. Let me give you an example. For distance, we're all familiar with distance measured in feet. Okay. Now, if I say, rather than feet, I want to know how many yards that is. What's the conversion between feet and yards?
3 feet each yard.
Okay, so each yard is 3 feet, or 3 feet is 1 yard, or miles. A mile is 5,240. Yeah, I knew it's 52 something. Feet is a mile. And so you've got to know these conversions in your head. You've got to know specific ratios, right? For the metric system, all you need to know is the base unit and then the prefixes. There is no weird combination. It's either 1, 2, 3, 4, 5, 6. So it's 1/1,000,000th is a micro of whatever it is. If I say I have a micrometer, I have 1/1,000th, or excuse me, 1/1,000,000th of a meter. A millimeter is 1/1,000th. 1/1,000th. Okay, it's important. It's 1/1,000th of a meter. A centimeter is 1/100th of a meter. And so, I know you don't get too close to someone when they're doing this. Either German, Hebrew, or less than 1, the tenths, hundredths, thousandths. Okay, you need that emphasis to make sure you're saying it right. So, on this chart, the ones that they've highlighted are the ones you have to know. You have to just have them memorized. The milli, centi, and kilo. Now, it's kind of a weird thing that if you notice, everything up here is less than 1. It's less than 1 unit, a tenth, a hundred, a thousandth, or millionth, right? And they're all lowercase. Then those that are greater than 1, 10, 100, 1,000, and millionth, they're all capital except for kilo, which is the one you have to memorize. It's a lowercase. You got to get the casing right, and that's why I changed the font on the slides, because originally the font I used was all capital, and it was not clear when lowercase and uppercase were being used. So, a milli, a centi, and a kilo. A kilo is 1,000 of whatever you're talking about. A kiloliter is 1,000 liters. A kilometer is 1,000 meters. Okay? A millimeter is 1/1,000th of a meter. A centimeter is 1/100th of a meter. And so we not only need to conceptually understand those, but remember what they stand for, because we're going to need to convert between units. If I have 100 centimeters, that's the same as 1 meter, right? If each one is 1/100th, then 100 of them makes 1. 100 times 1/100th equals 1. Same with a millimeter. If I have 1,000 millimeters, it's equivalent to 1 meter, because I have 1,000 of 1,000ths of a millimeter, of a meter, excuse me, which therefore when you multiply them together, it gives us our conversion. We're going to do that. Let's rewrite this. Rewrite 327 milliliters in terms of kiloliters. We're going to walk through this conversion together. Using the chart, you've got that in front of you, converting from a number of milliliters into a number of kiloliters using the numerical value of the units. Looks something like this. If 1 milli, right? The table says a milli is worth how much? 1/1000th. So it's 0.001. Okay? A milli is worth 1/1000th. So 1 milliliter is equivalent to 1/1000th of a liter. Got that? I mean, that's just from the definition on the table. That's all I've done. So if a milliliter is worth 1/1000th of a liter, how much is 327 milliliters worth? And for right now, let's just take it into liters, because I've got milliliters to liters. Well, 327 milliliters is 327 times 1/1000th of a liter, because it's a milli. 327 milliliters. Do you see that? Milli is worth 1/1000th, so 327 times the milliliter. Again, if you notice over here, it's 327 what? It's 327 milliliters. I rewrite that as 327 times milli, 1/1000th, of a liter. And I do the math. 327 times 1/1000th is 327 thousandths of a liter. But I wasn't asked for liters. I was asked for kiloliters. So now we need to know another conversion, don't I? 1 kilo is equal to 1,000. So 1 kiloliter is equal to 1,000 liters. Here's the trick on this one. You're not converting from kiloliters to liters, you're converting from liters to kiloliters, right? So the way the chart is set up, 1 kilo is worth 1,000. So 1 kiloliter is worth 1,000 liters, but I'm going from liters to kiloliters. So I need to reverse the logic and say, since 1 kiloliter is worth 1,000 liters, then 1 liter is worth 1/1000th of a kiloliter. See the difference? If I have a kiloliter, it's a big unit. I take 1/1000th of that. That's equal to taking 1/1000th of that 1,000 times. Okay. If we were converting, well, we wouldn't need this step otherwise. So we've got to put this in the units we have. We have liters. We need to know what is 1 liter worth in terms of kiloliters. We know we've got 0.327 liters, and each one of those is worth 1/1000th of a kiloliter. And so we do the math again. 0.327 liters is equal to 0.327. A liter is the same as 1/1000th of a kiloliter, and we do the math. And so our answer is we have 0.00327 kiloliters. Or later on, we do it in scientific notation. That would be 3.27 times 10 to the negative 4th kiloliters. Okay. Yes, sir.
It's the same as doing the King Henry chocolate milk or whatever.
Doing the what?
It's King Henry diagram chocolate milk or whatever. It's the different. The K is the kilometer, and every time you move over, you just move the decimal.
Mm-hmm.
Okay.
Mm-hmm. Yeah, so if we did this, see, we're moving this over 3. So 1, 2, 3. And then process here, 1, 2, 3. So that's a shortcut. But this this kind of logical process is going to be important to you when we do the next section. So yeah, this is one way of doing it. If you have that shortcut, I've seen it like in a acrostic or a chiasm. People know, okay, if I move down 2, I move it this many places. That same basic concept. But it's nice because everything in the metric system is a base 10, and you can do that. Since it's either a tenth, a hundredth, 1,000, or 10, 100, 1,000, you can move it decimal places and it works. If it was a US system, okay, from inches to feet, okay, it's 12 per 1. You know, it's not simple base 10. It's not as easy as moving the decimal place, which is why the metric system is so much easier in science and math. It's so much easier. Okay. But given that not everything follows a nice base 10 paradigm, there are things that we do all the time in here where this concept of how to convert from one thing to another is important that you understand. So, for example, we're going to be talking now about converting between units, the factor label method. What does that mean? Well, you can see in the book, and they detail this more over on page 10, that whenever you're converting between, you're given a certain unit, and you want to produce a certain unit, you need to have something that's going to convert it. We just said a moment ago, you know, inches to feet. My conversion is going to have something to do with the fact that 1 foot is worth 12 inches. So that is called a statement of equality. And I don't want to get ahead too much, but that's the idea we're going to drive for. So we have a given and some conversion factor that's going to produce what we want, what we've been asked to produce. That conversion factor is going to be made up of different units. Again, if we're converting to from inches to feet, if we are given inches, then we want some units here that are going to be feet over inches, because mathematically we need the units to cancel and we need the coefficients to work. So if you're given certain units, your conversion factor is going to be in the units that you want to end up with divided by the units that you've been given, this given units, in order to give you the units you want to convert into. Like, for example, this conversion factor comes from what's known as a statement of equality. You're going to have something that equals something. You have to know an equality. I use an example here of converting pieces to dozens. Okay? If I'm given pieces, like here's a bunch of Legos. How many are there? There are 8 Legos. Okay, how many dozens is that? You might be able to do that quickly in your head, but again, let's figure out the concept, because you're going to do a lot of things that aren't that intuitive. So, 1 dozen. I need to know that 1 dozen is equal to 12 pieces. If I know that 1 dozen is equal to 12 pieces, I can do the math. Why? Because that statement of equality could be written as, if I'm asked for dozens, and I'm given the number of pieces, it's the number of pieces times how many dozens relate to how many pieces. In this case, 1 dozen equals 12 pieces. And here's the concept behind these conversion factors. In math, we learned numerically the principle that anything divided by itself is equal to what? 1, right. It's a statement of unity. It's this and this are the same, and if I divide something by the same thing, it equals 1. Okay? That's the principle behind this. The conversion factor says, which is worth more, 1 dozen or 12 pieces? And you say, they're the same thing. Okay. If I divide something by something that's worth the same, what should the value be? 1. Okay. What we're converting here is not the amount, but the units that are involved. Basically, we're translating between one language and another. If you speak 2 languages, if you're bilingual, you say something in one language, then you come over here and you say something in another language. You've said the same thing, but it doesn't sound the same. Okay? If I have 12 pieces, and you tell me that And I know that 12 pieces is 1 dozen. And I said, you know what? Give me a dozen. No, never mind. Give me 12. And you go, it's the same thing. Yeah, but remember, every number has to have a unit. So did I ask you for dozens or did I ask you for pieces? Whichever I asked you for, that's what I need the answer in, that set of units. As a matter of fact, here's the other way. We could also say pieces are equal to the dozen times pieces divided by dozen. Notice here, when I look at the units, I've got pieces times dozens per pieces. Do you see that when we do the math, pieces cancel pieces? It's important. Just as we did the other day. Let me put up the screen. Let's do it. Sometimes easier said than done. Okay, so if I were to say 5/9 times 9 equals something. You could go through and say 5 times 9 is 45 divided by 9 is 5. Or you could go, you know what? 9 cancels 9 and they become 1. 5 divided by 1 is 5 times 1 is 5. Right? Same process. Here, let's say that I'm given 12 and I want it in dozens, and I know that 1 dozen, let me use the units. 12 times 1 dozen divided by 12, let's say these are each, okay? Each cancels each, 12 cancels 12, and if I have 12 pieces, I have 1 dozen. A more complicated thing might be, let's say that I've got 8 of something, and I know that 1 dozen of something is equal to 12 of that something. When I do the math, in science, units cancel units just like numbers cancel numbers. If I have each divided by each, they cancel each other out. So I can get rid of the each and the each, okay? When I look at the units, what units are left? Every factor has a unit, right? Because 8 means nothing, but 8 pieces, or 8 of each, means something. 8 pieces times 1 dozen is 12 pieces. How many dozens do I have? You see that each cancels each, and so the only units left are dozens. So this conversion factor is going to give me an answer that has a units of dozens. So I'll go through now and do the actual math. 8 times 1, 8 divided by 12. Or I could have simplified this to say 4 goes into 8 twice, and 4 goes into 12 3 times. So my answer is 2/3. 8 pieces is 2/3 of a dozen. And I know it's set up right because eaches cancel eaches and leave me with a unit of dozens. On the screen, describe 42 eggs in terms of dozens. Let's do this together. So we have 42 eggs. How many dozen eggs is that? Your statement of equality. 1 dozen eggs is equal to 12 eggs, right? So I can create 2 conversion factors from this. If I need to, I can say 1 dozen over 12 pieces, or I could say 12 pieces over 1 dozen. Because they both are the same thing. Something over itself, just said a different way, but exactly the same, gives me a multiplier of 1. But all that's really changing is going to be the language that it's in, the units that it's in. So in this case, 1 dozen eggs is equal to 12 eggs. So my given units times my wanted over my given is going to convert it into the language of my wanted units. I've been asked for dozens, right? So 42 eggs is what I've been given, times a conversion factor that has the units I'm looking for, in this case, dozen eggs, over the units that I've been given, individual eggs. In this case, eggs cancels eggs, leaving me with dozens of eggs, which has to be the units of my answer. Eggs, and again, it's written sideways. It's like this, 42 eggs times 1 dozen eggs divided by 12 eggs equals eggs cancels eggs, leaving me with dozens of eggs, which means my answer is going to be in the units of dozens of eggs. That's going to be my units, because I work the units first to see, hey, if I set it up this way, I'm going to end with dozens of eggs. Is that what I've been asked to solve for? Describe in terms of dozens. Yes, that's what I've been asked to find, so my setup is right. So we're going to do the units first, and then go, okay, now that I know it's set up right, do the math. 42 times 1, 42 divided by 12. And again, however you do that math, by reducing it down. But ultimately, 42 times 1 divided by 12 is going to be 3.5. And that's why the answer is 3.5 dozen eggs. Which is worth more, 42 eggs or 3.5 dozen eggs? They're the same. I've just converted it to a different language. Yes, sir?
Would you like it in decimal or?
We're going to go to decimals. Just about everything here decimal, because we're going to have to use that number to compute something else as we move on. We've already done this one, so it's just the same thing we've done, just laying it out in the same process. Looking at example 1.1 in your book. You can follow along with this, not a lot of notes. Just follow along with the logic from the book and on the board as we go. So we're given 14,000. Well, the question says, a student measures the mass of a rock to be 14,351 grams. What's the rock's mass in kilograms? So this is my given, 14,351 grams. I've been asked to convert that into the language of kilograms. Change the units. So my statement of equality, I'm going from grams to kilograms. I need something that says something grams is equal to something kilograms. And based upon the prefix, you should already know, because you have to memorize it, that 1,000 grams is equal to 1 kilogram. I'm going to create a conversion factor from the statement of equality. 1,000 grams over 1 kilogram, or 1 kilogram over 1,000 grams. That's going to be my conversion factor. Comes from my statement of equality. My conversion factor is going to be in the form of my wanted units over my given units. What do I want it to be in? I want it to be in kilograms. What am I given? I'm given grams. So my units have to be kilograms over grams in my conversion factor. And then we apply that conversion factor with the given times the conversion factor, puts it in the language of your wanted units. Which means, again, this is all in your textbook on the bottom of page 11, so don't feverishly be writing. It's all in there. But 14,351 grams times 1 kilogram divided by 1,000 grams is 14.351 kilograms. Notice the units. Grams divided by grams cancel each other out. I'm left with kilograms. That's my unit. Doing the math, 14,351 divided by 1,000. Using the shortcut, I'm going to move the decimal place 3 places to the left. Where's the decimal place? It's implied to be right here. 1, 2, 3. That's my answer. 14.351 kilograms is the same thing as 14,351 grams. It's now just in different units, and we got there by using this conversion factor. And we are almost completely out of time. So let's go ahead and not go to that. Let's go ahead and take a breather. Yes. This concept of conversion factors is something you're going to need the entire course. Okay? You're going to have to get this concept of how do I take something and convert it into something else? How do I, and right now we're just talking about changing it between one unit form and another unit form. But later on, when we're doing stoichiometry, for example, and I'll refer to that a lot because once we get to about module 8 in your book, it's going to say, okay, now we're ready to do chemistry at module 8. I mentioned before that I have a background in martial arts from the Naval Academy. Okay. There is one perception of the martial arts when it comes to the belting system that people are striving and striving and striving and striving to one day become a black belt. Okay? But within the martial arts community, they realize that once you become a black belt, now you're ready to learn the martial art. Everything prior to that is making sure that you understand the language, you understand the concepts, but at that point, you're finally ready to do chemistry. In this class, we start doing chemistry proper the second half of the class. The first half of the class is just to give you the grammar, give you the terms, give you the concepts, so we can get there. Okay? And you're going to need this idea of using conversion factors, the principle of it, through the entire course.